A very good afternoon to one and all. I, Ms. Shefali Rahul Gutke, would like to welcome you all for today's guest lecture on Introduction to HECRAS Software. I kindly welcome to today's speaker, Mr. Vignesh Iyer, Associate Engineer at Stantc, Pune. Sir completed his graduation and post-graduation from Pune University. Sir takes pride in providing innovative and creative solutions on his project, and North Huston Bike Park is one such project where he has contributed right from the project conceptual stages to providing construction design documents. Sir has a knowledge of various softwares, which includes Civil 3D, Storm Design, ArcGIS, Sanitary Analysis, HECRAS, HEC-HMS, Autodesk InfraWorks, Bentley WaterGems, and Water Seaver. So I request Sir to please proceed with today's session.
Okay, before starting, would like to mention a few things. Sir, it is really very interesting to come across your profile and you are providing such a unique consultancy services. So first of all, sir, thank you very much for being a part of our department and granting us your time, giving us your time and granting us our application. First of all, sir, thank you very much on behalf of Department of Civil Engineering. And I request ma'am. I request sir to proceed for the lecture.
Sure.
Again, on the same time, students are appeal that such kind of content is not available in our syllabus. So pay attention and whatever the gaps we have identified and whichever the subject which is associated, which is helpful for mapping. So pay attention and in the end, we will like to have the question answer session. Whatever doubts you are having, I request all to note down. Okay, students? Please pay attention. I request I also to please start the presentation.
Sure. Thank you. Thank you so much for having me here today. I thank Mr. Amay Kedikar, Honorable HOD, Department Civil, and Ms. Shefali Gutke, ma'am, Professor and Expert Lecture Coordinator, for having me here today and allowing me to present to you guys a topic on HECRAS, which is one part of water resource analysis, so that I can share my experiences as well as the software knowledge with you guys. Thank you so much. So basically, thank you for having me here first off, and I'm Vignesh here. I have around 7 years of experience working in this field, and today I'm going to present the topic of HECRAS, which is a software used for flood mitigation and other water resource computing purposes. So I hope you guys can see my screen, and this would be more of an interactive session wherein if you don't understand anything or if you have any questions in between, you can interrupt me and ask me whenever you are not comfortable or you're not understanding any concept. So that way, even I will be able to uh, get you more information or maybe uh, show you different examples, probably take you to a different route whenever I'm explaining the topic. Okay. Am I audible to all?
Yes, sir.
Okay, thank you. I hope you guys can see my screen.
Yes, sir.
Okay, so moving forward, let's get started with introduction to HECRAS. So basically, before giving an introduction to HECRAS, I will start up with uh, some of the hydrology and hydraulics basics. So for today's agenda, it would be getting started with basics of hydrology, hydraulics, then introduction of HECRAS, and then basically how and what computational procedures the software uses uh, for the model computation for analysis. Okay, thank you. So let's get started with through some basic definitions. Uh, so can anyone tell me what is hydrology and what is hydraulics? Anyone. If anyone has any topic, or I mean, if they can judge by whatever I've written it here. Okay. So basically, hydrology is taking rainfall and converting that into runoff volume. So the storms, the rainfall event that you guys see. So it's the precipitation which then converts into a volume. So hydrology is nothing but it is basically taking that rainfall and converting that into a runoff volume. When I say runoff, I'm talking about it with respect to time. So that is flow or discharge. Okay. And hydraulics is nothing but it takes that same runoff volume and converts that to elevations. So basically, when you get precipitation, uh, it that gets converted into runoff volume, and that runoff volume, when it get converted into elevation, which is like elevation of water level, and in conjunction with that, basically that is hydraulics. So uh, with respect to hydraulics, I can say that water surface of the hydraulic grade line, in open channels is the water surface elevation or the flood elevation, and in pipe systems it is the hydraulic grade line. Okay. So I hope the basic definition is clear to one and all. And just so we move on to the different uses of hydrology and hydraulics. Um, so, like I just mentioned, I've walked you through the basic definitions. So, with that, moving forward with the uses. So basically, uh, where it is used to for those applications, and basically the application and the uses that covers the planning and design of flood reduction facilities. So what is flood? Basically, when the banks of the river gets more volume of water, it gets inundated, and that's why it goes beyond the banks of the its river course, and it in turn turns into flood. So planning and design of flood reduction facilities. Um, so if you are designing any reservoirs, detention systems, even channel improvement projects, so that way, and then levees to protect the areas which are flood prone. Um, then operating and evaluating existing drainage facilities. So basically, operations to see if a project is working the way it should be for permitting and regulation purposes. Um, like preparing for responding to floods. Uh, Using those analysis and things like that, you can you can define a level beyond which it would turn catastrophic. It would be very crucial to make sure that you're preparing, and you're having the telemetry in place so that it gives the right siren at the right time, and preparing and responding for the floods. Uh, the hydraulics part would then be the flow in the reservoir. So basically, um, equation to determine how much water can discharge out of the reservoir at a given amount of time, um, improving the drainage, regulating floodplain activities, and so that would be the combined application or maybe uses of hydrology and hydraulics. Um, so now moving forward to some basic concept, which I guess we have learned from schools. So I hope everyone can recognize this drawing this year. Can anyone tell me what is this, or where does this chart start? Anyone?
It is hydrological cycle.
Yes. Thank you. That's rightly said, Ratan. So basically, this is a hydrological cycle which we are, I mean, learning from the time we were kids. So basically, it starts from the rainfall. So going back to the basics, um, so it starts with condensation, then rainfall, and then again water seeps into the earth, infiltration, groundwater flow, water tables. I mean, adding to the water table, stream flow. Stream flow is nothing but runoff, and then eventually getting added to the water body again. So this is what it is in a summary point of view. So basically, hydraulic in here is with respect to the time that has been developed in the hydrology, and the hydrologic processes that determine for a given amount of time rainfall how much water gets to a point on a stream, and at what time by uh, it reaches to the runoff, or it gets converted from runoff to elevation. So by contrast, the hydraulic processes that takes this volume of water with respect to time and then determine how high the water will rise in the stream. Getting my point? So this is nothing but more into what we are looking now in water resources. So this diagram we have learned from the time we were kids, and but now if you look from the water resource point of view, then basically the rainfall, the precipitation is nothing but the hydrologic cycle or the hydrology, and hydraulics, it takes again the volume of water, the stream flow, everything, and uh, with respect to time, and then determine how high the volume in an open channel or any stream flow would uh, increase in the particular stream or channel. Okay, so that is something that you should note. Again, moving to the next slide, these are some of the major hydraulic and hydrologic components, uh, like precipitation, abstraction, losses. So how many types of losses are there? There are evaporation losses, there are infiltration and other losses. And evapotranspiration is also there. Um, then rainfall, runoff, transformation. These all come into hydrology or hydrologic components, stream flow and reservoirs, which eventually leads to stream flow and reservoirs. Okay. Now, when you look into the hydraulic part of view, uh, so hydraulic point of view, it has the downstream conditions that will affect the upstream because of the step back water. Uh, because the step back water, it can only see what is downstream of it. Okay, so major hydraulic components of the downstream condition, the channel geometry, or the stream geometry, the slopes, any structures, weirs, bridges, culverts, dams, which are on the way of the streams or maybe big rivers, and uh, basically the input for hydraulic is the flow from hydrology. Okay, so I hope I'm going with my pace is okay. I hope I'm not hurrying through my through my slides. Okay, so I hope up till now everything is clear, and we now move to a different concept that you guys have learned probably in engineering now, which is watershed and drainage basin and watershed analysis. So, what exactly is a watershed? Can anyone give me an idea of what is a watershed? Anything like that? Okay. Uh, Not an issue. So basically, uh, this is where all the basic concepts or the components start, which is the watershed. The orange dotted line that you see here is uh, nothing but the ridge line. Uh, in a topography, and it everything falling into that orange dotted area will contribute to the stream which is shown in blue. Okay, and out of the orange, I mean, out of the orange area, which is, I mean, outside the ridge line, you will see a different watershed that will be contributing to a different stream flow. Okay, so in this picture, this blue line that you see is the stream flow, and I hope you also might have heard of time of concentration or anything related to that. If yes, then please raise your hands. If not, I will just explain it to you guys. Anyone who has heard time of concentration? Okay. Okay. All right. So basically, as I explained now, this is a watershed, and whenever a drop of water falls into this orange zone in any part of the watershed, it basically takes time from uh, traveling from the upstream point of the area to the downstream point where the blue line meets the road in the picture. So basically, the time taken by the drop of water from reaching from the farthest end to the outlet. In this case, it's the streamline which is ending at the road. That's the amount of time taken by the water to reach there, and that is not only, I mean, it is called the time of concentration. So basically, this also plays an important factor whenever you're doing the watershed analysis or maybe any water flood analysis. This plays a crucial part, and I tell you why. Uh, Recently, you might have also a couple of years back, you might also have heard about the Kolhapur floods and all. Uh, that's because of the uh, river inundation and things like that. But if you see, most of the floods that happen is due to the increase in concrete cover. Um, so when I talk in terms of increase in development and effects of development, let's just see this graph. Uh, Let me quickly talk about the effects of development and how it occurs, uh, and what effect a development has over a certain grassland area or maybe no developed area uh, on Earth. So basically, as development occurs, the graph itself says that with respect to time, the flow increases. Okay, so any development that is occurring into a particular area which was, I mean, which didn't have any development before. So basically, what happens is you're increasing the concrete cover in that area. So when you increase that concrete cover in that area, the basic infiltration ability of that land gets reduced. What is infiltration? The ability of the land or maybe the water to seep into the ground is nothing but uh, infiltration. So when you add a concrete cover to it, it is impervious. So basically, when you add more impervious cover, there is less permeability or less infiltration into the ground, which not only increases the uh, runoff volumes, but also makes it, I mean, also results in increasing the water surface elevation in that area if you don't have a proper drainage system in place. So basically, any increased cover or increased area reduces the permeability, infiltration. Everything goes in hand, so which in turn uh, increase the runoff volumes. So also here, one thing also comes in picture is the Manning's coefficient. If you guys have heard about the Manning's, so basically for smoother surfaces, the response time is fast, right? So basically Manning's coefficient, it depends on different surfaces. A rough surface has a different Manning's coefficient. Smooth surface has a different Manning coefficient. And can anyone tell me what effect does a Manning coefficient has over flow? Quickly. I hope everyone are from the civil engineering team and um, could be second, third year, or fourth year people. So quickly, just tell me what effect has a Manning coefficient over the flow? No one? Okay, not an issue. So basically, what Manning is, when the Manning coefficient increases, so there is much friction on the surface, and hence the flow decreases. And when the Manning coefficient is it decreases basically for um, smooth surfaces, there is faster response time. The time of concentration is very less, and the time taken by the water from the upstream to the downstream to travel from the upstream to the downstream end is very quick. So that in turn increases the volume of the discharge that you're saying. So Q is inversely proportional to the Manning's coefficient, and any faster response time is nothing but it's a result of smoother surfaces, and improved drainage also can lead to faster response time and more uh, more addition of stream flow or the runoff into a water body. So a fill in a floodplain or a fill in a area is due to less floodplain storage and faster response time. So that is one of the reason whenever we are developing any pervious area and making it impervious, we also need to take into account the effect it has on uh, the surrounding areas, the downstream side, as well as uh, the overall effect it has over the flow with respect to time and the flood. It also contributes to a flood to a certain extent, uh, which is shown in the diagram here. Um, so this is a house which is first built in very high ground, and as water level increases, it eventually uh, puts the people here at risk. And with increased impervious cover, the water then increases to the level of the ground here, which is uh, what we see in floods. Okay. So now I hope at least I've given you a picture of the basic understanding of water resources, hydrology, hydraulics, and let's now jump into HECRAS. Uh, so HECRAS is nothing but it is a software. It's developed by the U.S. Army Corps of Engineers. So HEC stands for Hydrologic Engineering Center, uh, which is based out of California, and RAS stands for River Analysis System. So basically, what it does is it analyzes a network of natural and man-made channels and computes the water surface profiles based on study one-dimensional flow, hydraulics, includes composite channels, supercritical to subcritical flows. Um, then you can also have multi-waterways, bridges, culverts, etc. Into this. So stable channel design, um, bridges, culvert options, and then stable channel design as well. So basically, the software allows you to perform steady flow, water surface profiles, unsteady flow simulations, movable boundary, water quality analysis, and wherever the water profile changes very rapidly, basically it uses HECRAS uses the computational energy equation, and whenever the water surface profile changes very rapidly, it uses the momentum equation. I hope you guys are aware, since you are an engineering student, you might have come across this momentum equation as well as the uh, continuity steady flow equations in your syllabus. So the basic computational procedure of HECRAS for steady flow is based on the solution of one-dimensional energy equation. The energy losses are evaluated by friction and contraction expansion, which I will come in a minute. Um, so, like I said, already I've mentioned the momentum equation may also be used in situations where the profile changes very rapidly, as in case of a hydraulic jump, or whenever there is a obstruction or like bridges, things like that, and evaluating profiles of a river confluences. In those contexts, the momentum equations can be used. So this is nothing but the uh, computational procedure which I explained to you guys. Um, so can anyone tell me if they have come across this in their syllabus or not? Because I won't be explaining this in detail, since you guys have already covered that in your syllabus. So basically, this is nothing but the energy equation. Um, so water surface profiles. There is a section one with a datum, a depth, and water surface for you, and then there is a section two. So if you take two sections across water body, you will have two different depth of water, which is y1 and y2. Uh, z1 and z2 would be the elevations from the main channel inlets. v1 and v2 are average velocities, that is total discharge by the total flow area, and alpha 1 and alpha 2 are nothing but the velocity coefficients. G is gravitational acceleration. And what is HE? Can anybody tell me what is HE? And this is quite simple. Okay. Um, so basically, that's head loss. Uh, if you didn't know that, so HE is energy head loss. Um, so one-dimensional energy equation, uh, energy loss friction, Manning's equation, contraction expansion, losses coefficient, and these all things come into picture. Uh, basically, it is nothing but uh, it uses the one-dimensional steady flow hydraulic model, which is very helpful for hydraulic engineers for channel flow analysis and floodplain determination. Um, if you guys recall from hydraulics, steady flow describes condition in which what is steady flow basically? It's which conditions in which depth and velocity from I mean it is steady flow describes condition in which depth and velocity at a given channel do not change with time. It is with respect to time. So uh, that is steady flow. Then GVF is nothing but gradually varied flow. Gradually varied flow is characterized by minor changes in the water depth and velocity from cross section to cross section. So HECRAS uses basically the primary procedure that HECRAS uses is to compute the water surface profiles, the M1, M2 profiles, that S1, S2 profiles that you guys might have learned in your syllabus. So it basically computes that water surface profiles and assumes a steady GVF flow scenario, which is also called as a direct step method, the computational procedure. So the basic procedure is based on like the iteration for the energy equation that you can see here, uh, which states that the total energy at any given location at a stream is a sum of potential energy and the kinetic energy. Okay, so here in this equation, potential energy is datum plus depth from inward. I mean z plus y. That's the potential energy, and kinetic energy is alpha v square by 2g. So this is what it is. So uh, the total energy at any given point is the summation of potential energy as well as kinetic energy, and the change in energy between these two cross sections is called the head loss. So I hope I'm clear. And given the flow and the water surface elevations at one cross section, uh, this direct step method computes the water surface elevation at the adjacent or the other cross section that is taken into consideration, and whether the computations proceed from upstream to downstream or downstream to upstream, depending on the flow regime. The It also characterizes the Froude number, uh, where Froude number less than 1 is nothing but the subcritical flow. Froude number which is greater than 1 is supercritical, and equal to 1 is denotes the critical flow. Okay. So I hope I'm clear, and let me quickly walk you through how this direct step method is calculated. So let's just say you assume the water surface elevation at the upstream section, okay, or downstream if it's a supercritical profile. So whatever known information you have, uh, you keep it with you, and you assume a water surface elevation for the second section, which you don't know. I mean, you don't know any parameters on the second section. So based on whatever assumptions you had, based on the water assumed water surface elevation, you determine the total conveyance and velocity head. So what is conveyance? Conveyance is is denoted by K, which we'll see in further slides, and the velocity head. And then you assume a water surface elevation at the upstream cross section. If it's a um, subcritical or critical, and based on the assumed water surface elevation, determine the corresponding total conveyance and velocity. Okay. So with that, I mean, after determining the total conveyance and velocity head, you compute SF. So what is SF? SF S0. Probably you might have come in contact. I mean, come in with those terms while you're second engineering fluid mechanics probably. So that is nothing but the base loop and the frictional flow. So when you, with the values of the conveyance and the velocity head, you compute the friction slope, and then you solve the equations. So basically, after solving those equations, the value you get, um, you compare it with the water surface at section 2, water surface profile at section 2, and if it's coming, I mean, close to the assumed value, that is close to 0.003, that's the tolerance defined. So if it comes close to that value, then probably you are moving in the right direction. Okay, and then you compute the frictional slope and solve for the losses in the energy equation. Okay, so we now move into the flow classifications, and this is the basics of fluid mechanics: the steady flow, uh, unsteady, uniform, varied flow, things like that. So um, I hope I don't need to explain these basics to you guys. This is what it is, and this is pretty much clear. Uh, just to quickly go through it, steady flow is a constant flow. Classification by distance, uniform, characterized by constant depth and constant mean flow velocity. Non-uniform is characterized by varying depth. So things like that. And just quickly moving to the next slide. Now we have the momentum equation. Uh, so this is what the momentum equation looks like. When you differentiate velocity, I mean, the equation here is nothing but what we have it uh, in this equation. Only thing is it is a derivative of this differentiation. So basically, the term here is local acceleration and convective acceleration. Then we have the pressure and the gravity forces and the friction forces. So now if I have to divide it into three different categories, uh, kinematic, wave, diffusion, and dynamic. So kinematic is the one wherein the gravity forces are predominant and come into picture. Diffusion is combination of gravity and pressure, and dynamic is where all the forces uh, comes. I mean, both the inertial as well as the pressure forces comes into picture, and the backward effects are negligible, like from M1, M2 profiles, basically. So this is nothing but I've bifurcated the equation into three different uh, forms, which is kinematic, diffusion, and dynamic. So the understanding of this is very much crucial whenever you're analyzing any uh, water body or any analysis of flood. Basically, you can get a quick idea, and wherever the water surface profiles is changing very rapidly, uh, you can uh, use this equation. The momentum equation comes into picture. So that's the bifurcation that I've said. If you guys have any doubt, if you are not understanding anything, please raise your hands. Let me know so that I can explain you better. Now, I mean the same thing. If I have to say in a different way, uh, it's a steady, uniform, steady, non-uniform, and unsteady, non-uniform flow. Okay, so and those parts which come predominantly into picture is for steady, the base slope as well as the friction slope are the same. Steady non-uniform flow comprises of these terms and values, and unsteady non-uniform flow is the whole equation, momentum equation here. Uh, Further looking down into the computational procedures, so what I've shown here is cross sections and water surface profiles. Um, so, like I said, flow conveyance comes into picture. The equation that you can see there, it's nothing but the Manning's equation, and basically, the water surface profiles are computed from one cross section to the next by solving the energy equation, um, which you call it the standard step direct step method. The energy equation, I mean, when you analyze any streams in HECRAS, so basically what you do is you take cross sections over those streams, and you make sure that you define for the cross section that you have taken, you define the values for the area, the Manning's parameter for that, as well as the conveyance. So basically, in the picture to the right, you can see there are two streams are coming and meeting at one. So whenever you take a cross section, you should be knowing at least a few of the parameters in that cross section, which is nothing but the channel center line and bank lines. This is the leftover bank, this is the right over bank. So um, if you guys are interested, we can move more into computational procedures and have a different session which would be focusing more into analyzing a small flood stream or a stream for flood analysis or something like that on HECRAS 1D analysis. Just to start with it, to give you an idea, you can also have your B thesis on HECRAS, which is also a freeware software. You can have those computations and create uh, a good informative thesis as well as a presentation on that based upon the flood uh, details that you have carried out in HECRAS. So, uh, whenever you cut a cross section of a channel, this would be what you can see. The main red lines that you see, it's nothing but the channel, the main channel, and the blue lines, the extents from the red, is nothing but the left as well as the right over bank. Okay, so and it's not necessary that all the flood plain or the flood banks would fall into same surface, or maybe the coefficient for all those surfaces manning coefficient would be the same. It might come as clay plus rocky combination, as well as different flood surface uh, things, wherein you have to assume different n values for that. Okay, so this is the A is nothing but the area. Okay, the n is the area for the main channel, n is the Manning's coefficient, p is the perimeter for that particular section. When you divide a cross section into different sections based upon the different Manning's coefficient, you get different areas as well as different parameter values as well, which in turn help you in calculating the conveyance factor, uh, which is then used to calculate the Q. Okay, so this is the basic computational procedure that we could see. I hope you guys are getting an idea of how a floodplain is analyzed by drawing different cross sections. Yes, this green line that you see here, those are nothing but cross sections, uh, and I mean the result is more fine if you take if the number of cross sections over a stream are more. So basically, if you take two or three cross sections over a reach, or over a length of a stream, it could happen that your results would be very crude. Uh, the actual scenario as well as uh, the your results might vary a lot, but having multiple cross sections over a stream would help you get those values very accurate. So it's nothing but iterative method, and this not only helps in having an accurate analysis, but also gives you an idea how the bed of the channel, or maybe how the channel changes itself over its length. Okay, uh, moving on to floodplain delineation. So, like I've shown you in the previous slide, uh, the main channel, which was shown in red, it's the channel which is like solid hatch, a solid blue line that you can see here. That's the main channel. Okay, the channel and the floodplain are both integral parts of the natural conveyance system of a stream. Okay, so the floodplain carries flow in excess of the channel capacity. So this is the delineation for 10-year flood. This is for 100-year flood, and it goes on. I mean, basically, if you see the recent floods in uh, Delhi, or maybe uh, a couple of years back in Kolhapur, it it's because of the Panchganga river. So basically, the river flows like this, and suddenly, if the storm event increases, and which results in greater runoff, so the water moves beyond its bank, and it inundates into the area surrounding the main river channel. So this is what uh, represents. I mean, if it's a 10-year storm event, then it would reach to a limit wherein it would inundate the area with respect to the storm event and things like that. And basically, this not only is a greater threat to the civilization as well as the human population, but uh, the very identification of all floodplain areas and flood risk zones is also important, where I mean, basically, you can tell which areas will go underwater, and this not only gives a good analysis, or maybe it also helps the human population and put uh, people away from harm's way. So, like I said, the channel and the floodplains are both integral parts of the natural conveyance of a stream, and the floodplain carries flow in excess of the channel capacity. So, the greater the discharge, greater the extent of inundation. Like I said, if uh, suddenly we expect, I mean, we get a storm event of 100 years, then definitely uh, the extent of inundation increases. And because of this, its devastating nature and flooding, it poses a serious threat to human population in many parts of the world. And hence, this is why flood analysis, flood mitigation is of utmost importance. Even urban flooding uh, can be easily avoided, or maybe not avoided altogether, but mitigated to some extent if you have done an analysis and if you have a knowledge of what extent to what extent the water would inundate in an area. Okay, so this is would just give an idea of basic principles in which HECRAS works on. So, like I said, the both um, channel I mean, the data requirements on which HECRAS works on is nothing but the channel description, the length of a channel, uh, the roughness coefficient, like I showed you in the cross sections, then the channel cross section geometry. So in the geometry, you would be pretty much aware of what area uh, would come into this zone. Say a zone, a clay zone, then the rocky zone, then the grassy zone. So whenever the flood goes, I mean, goes beyond its bank, it not only um, it not only what do you call it? So it not only just comes across one type of soil, but it also comes across different variation of surfaces, maybe grass, rocks, and anything like that. So channel cross section geometry, channel roughness comes into picture, length of reach, and for boundary condition, it's nothing but uh, flow stage or maybe stage storage data at upstream and downstream locations. And at last comes the structure geometry, pictures, sorry, bridges, culverts, and weirs, which play an important factor in a water body whenever you're building any bridges or culverts or any weir kind of thing over a body. It's nothing but a small obstruction. So that also um, affects the floodway or maybe the water body, the streams in a different manner. It anything like that would affect the water surface elevation. It might increase or drop depending on how you design it. So the picture here is again nothing but the Kolhapur floods that we saw, that we all saw, and you can see that it has actually taken over all of the area. Just those roads which are on the verge of also submerging, it's everything is underwater. So this is once in a lifetime. I mean, uh, happens not regularly, but definitely if climatic conditions as well as different uh, storm events give rise to such kind of floods. And we also know that many people lost their lives and things like that. So this kind of floodway mitigation analysis and things like that are at most important. And I mean, this is not usually being taught in our syllabus, but once you pass out and if you would like to make a career in that, then it's the best option, because moving forward, every everything would come down to water resource planning after the after a city or an area uh, reaches its utmost level of development, urbanization. So, like I said, this was this is something that the pictures or the previous slides that you saw is nothing but the output, the data requirements, the output, and for HECRAS. So HECRAS generates different outputs, like the one which gives you a 3D output the cross section output here, graphical tabular outputs as well, and water surface profiles, which is, I guess, you guys can relate to it, uh, depending upon the profiles, water surface profiles that you have learned in your college. Uh, so it gives you a 3D view of how the water progresses in a channel, with bank stations and the ground and the water surface profiles, how it usually, after computing, how it usually changes. And now in this figure down here, if you see, the bank stations are shown in red. So this is usually where the water uh, is the usual stream of water would flow. But then due to floods, it goes beyond its banks, and it inundates those areas, and the water surface elevation increases. So basically, again coming into the basics, uh, runoff to elevation is nothing but hydraulics, and whatever amount of water that comes into which rainfall to runoff, it's nothing but hydrology. So this not only gives you the extent of inundation in an area, but it also gives you the water surface elevation as well as the energy grade line in your cross sections. And just coming back to the water surface profiles, which is also an output of HECRAS. So this is nothing but the upstream, the sluice gate in a dam. Okay, upstream control, downstream control, and the hydraulic jump. Okay, so you can see that the flow, it changes from rapidly to GVF to again rapid, again to GVF. And if you also see the, I mean, if you have to also look into this from water surface profiles, maybe from point of view, then you can also uh, differentiate it into mild slopes, critical slopes, and steep slopes, wherein the base depth or maybe the normal depth is greater than the critical depth for mild slopes and things like that, and uniform flow, critical, subcritical, and supercritical flows as well. So this is how uh, it varies and it changes. Uh, this might give you an idea of how basically an analysis is done in HECRAS, and it is very much important to have this knowledge whenever um, you would be having. I mean, if you want to make a career in water resource, then definitely this is a must to have an idea of all this water surface profiles, the momentum equations, energy equations, which would play a different role uh, in building your basics. With this, I conclude this session, and the forum is open for questions.
Any questions? Any questions from your side, students? If you have any questions, you can ask.
Please feel free to ask any questions or any doubts that you might have, anything that you didn't understand on. If you have, okay, if you have different questions regarding career options after B in water resources, then you can also ask that. Not only pertaining to HECRAS. HECRAS is just a tool, but I just walked you guys through the basic understanding, because it's the input and the output. Anyone can do it. Anyone can work on HECRAS and get an output which would make others happy. But you should also get an understanding of on what basis the software works, because at times if the software doesn't work, you should be able to justify your output, or maybe you should be able to back up your findings or anything like that. So, which is more important. So that's why I walked you guys through the basic understanding of HECRAS. And if you guys are interested, then probably I can take a different session wherein I can walk you through a simple analysis of a stream, so you guys can get an idea of how HECRAS works and things like that. That would be a live session. Uh, you guys have to work with me on that if you guys are interested. Hello. No
Yes, sir,
questions.
you are audible.
Yeah.
I don't think
Students are
so, sir.
brilliant
They
here.
have any questions. Okay, sir. Thank you so much, sir, for delivering such knowledgeable lecture. And on the behalf of Civil Engineering Department, I thanks to our management, Vice Principal, Principal, and our HOD, sir, for arranging such type of lecture. And special thanks to Vignesh, sir, for giving your valuable time to us. So here I concluded my session.
Thank you. Thank you so much, Pam. Thank you so much, Amay sir, for having me here today. And if anyone is interested, do let me know for any future sessions. Thank you. Thank you so much.
Okay, sir. I'll ask them if they are interested. I'll ask to contact it to you. Okay, sir?
Sure, sure. Yeah.
Okay, sir.
Thank you.
Thank you so much, sir.
Thank you so much,
Okay.
ma'am.
Have a good
Thank
day.
you. Yeah. Bye bye.
Okay.
Take care.
Okay, sir.